Hey everyone, so let's solve this Leetcode hard problem, apply operations to maximize score. So before moving on to the problem statement, the prerequisites of this problem are you should be aware about the basics of a sieve algorithm. You should be knowing what binary exponentiation is and how do we find this previous or next greater element using stacks in order of n. So if you are already aware about these algorithms, then you will be able to easily apply them in this problem and will be able to solve it on your own. So if you're not, then try to learn these algorithms, learn all of these three concepts first, and then try to apply it on your own and see whether you are able to solve it or not. Okay, so let's see the problem statement. We are given an array nums of n positive integers and an integer k. Now we initially start with a score of 1 and we have to maximize this score by applying the operation at most k times. Okay, now in one operation what we can do is we can choose any non-empty subarray nums that we haven't chosen previously and then choose an element x of this with the highest prime score. Okay, what is the prime score we'll seeing. So we'll be finding out the element x which has the highest prime score, and if there are multiple such elements who has the highest prime score, we'll be choosing the one which has the smallest index. And now we'll be applying, means multiplying our result by this element x. Okay, element in the subarray nums. And here I hope the definition of subarray is clear, and the prime score of an integer x is equal to the number of distinct prime factors of x. So for example, if we have 2, then the number of distinct prime factors of 2 is simply 2. Suppose if we have 6, so it will be 2 to the power 1 into 3 to the power 1. So number of distinct prime factors here is 2, so hence the prime score of 6 is 2. Okay, so similarly, suppose if we have 300, so prime score is 3 because 300 equals to 2 square into 3 into 5 square. So the number of distinct prime factors are 2, 3 and 5. Hence the prime score here is 3. Now we need to return the maximum possible score after applying at most k operations. And this k can go up to the total number of subarrays that we have or 1e9. So obviously it will be bounded by the total number of subarrays. Okay, which will be of the order of n square, and n can go up to 1e5. So obviously it means iterating through all subarrays and then finding out the solution is not feasible. So let's first see see the input here. So we see the k is 2 and we have these as elements. So obviously the score that we have currently is equals to 1. Now since we want to maximize the score, so we'll try to multiply it by the maximum values possible. So let's try to simply take this subarray because it is the maximum value and we'll be able to multiply it. Since it is a single element, so the smallest means the prime number x with the highest prime score will be for 9, the prime score will be 3 square. So prime score is simply 1. But since the element there exists only one element, so this will be like the x that we'll choose. So we'll be cleaning up the score by 9 and will be means k now becomes 1. Now again we try to see whether we can use these for 9 further in further subarrays. So if we use it in this subarray, suppose 3 9, so we see the prime score of this subarray is also 1 because it is 3 to the power 1, and prime score of this element is also 1 because it is 3 square. So obviously if we choose this subarray, then if we are given that if multiple such elements exist with the highest prime score, we'll be choosing the one with the smallest index. So in this case we'll be choosing this 3 and the score will be simply becoming 9 into 3 equals to 27, which is not we are not able to choose 9 in this case. But suppose if we choose this subarray 9 3 9 3, so again we see the prime score of this is 1, prime score of this is 1, but since this is occurring earlier, so this will be the x that we'll be choosing, and in this case the score will be increasing by 9 into 9, and we have used two operations, so it will be the final result that we will be getting will be 81, and that is the maximum possible here. Okay, similarly let's try to see for another input. So we are given k equals to 3. Okay, we are given k equals to 3. So let's obviously we'll be choosing the maximum element first, so we'll choose this 19. Okay, as soon as we choose this 19, we see the score will be getting multiplied by 19. Now let's see whether we can choose these 19 multiple times or not. So we have 19 and 12. So the prime score of 19 is 1 only because it is 19 to the power 1. 19 is a prime number, and for 12 it is simply 2 square into 3. So the prime score is 2 here. So since this will be the x that will be getting chosen, so we will not be able to use this 19 multiple times. So k remains 2 now. So now let's try to see the next greater element that we can choose. So we can choose 18 as a single element. So we'll be able to multiply it by 18. Okay, now let's see whether we'll be able to use this 18 multiple times or not. So we'll have 10 and 18. So 10 is simply 2 to the power 1, 5 to the power 1, and it is simply 2 square into 3. No, sorry. 2 into 3 square. So again the prime score of both are 2 only, because we have 2 distinct prime here and 2 distinct prime here as well. So in this case also, since we both prime score of both the elements are same, so we will be choosing the earlier element, so x will be this. So we will not be able to choose this 18 multiple times. So now k has reduced to 1 and we have used 2 operations to increase our score by this value. So let's try to see for the next third greater value, which is 14. So we'll be choosing this value, which will be multiplying by 14, because we have chosen a single element, and in this case the maximum output that we'll be getting is the result of this value, which is 4788. Okay, 9 is 72 and 2 4 is 8, so yeah, 8. Okay, let's see another means so I hope like you are able to see how we are trying to maximize, means finding out the maximum prime score based on the prime factorization of this and finding out the number of distinct prime factors, and then we are able to see like how we are trying to maximize the score. So what will be like the most naive way of solving it? Naive way or like brute force? So brute force will be simple. First we definitely need to iterate through all the subarrays. Okay, we iterate through all possible subarrays. We find out the score, means the element that we'll be choosing in that particular subarray, and we push it in a suppose result. Okay, that this is the element that is getting chosen. So for all the n square n into n minus 1 by 2 subarrays, we'll find out this x and create a separate vector. Now we can simply sort this vector on the basis of decreasing order and choose what? Choose the top k elements. Okay, so we'll simply choose the top k elements. So what we'll do, we can simply iterate through all subarrays first. Okay, once we have iterated through all subarrays, find x of each subarray. Now we have find out the sub x of each subarray. How we'll find out the x? We'll find out, means for the current subarray, we'll find out the prime score of each element and then see like which is the highest prime score, and if they are multiple, then we're choosing the element which is occurring at the means earliest side. Okay, so we'll find its x, and we have created this vector result, vector int result, and we'll store it in our result. Now for all the subarrays, we'll be pushing the result, the x that we'll be getting. Now we can simply sort this result on the basis of decreasing order. Okay, so we can sort it on the basis of decreasing order. And once we have sorted it, what do we want? We want to maximize the score. So we'll be choosing the top k elements. Okay, the top k elements means means the elements from result of 0 till result of k minus 1. Okay, so in this manner we'll be able to solve this problem. Now how do we, like, what will be the complexity of this code and how will we find this x for each subarray? These are the questions that remain. So obviously, like, for iterating through all the subarrays, we'll be iterating for I from 0 to n minus 1 and then from j for I to n minus 1. Now we have the subarray I to j. What do we want? We want to find the x for this subarray. So for finding the x of this subarray, we should be aware like how many distinct prime factors of each number there are. Okay, so we know to find out this, we can like for each number we can means go till square root of that number and find out its prime factor in like each number. So that will be like means extra complexity, or we can use sieve for that. You can use sieve to pre-compute the results of this, like what are the number of distinct prime factors of each number. Okay, so we can use means we'll be using sieve. I will be showing you how we use it, and once we have it, we'll be able to, like, if we have already pre-computed this, then we'll be able to solve it in n square, because we'll be able to get this result in constant time, as we can maintain a running variable which denotes like the maximum high score that we'll having, and maintain this running value of this x. Okay, so either we'll be able to solve it in n cube, and if we maintain the running means calculation of this x, we'll be able to solve it in n square. So obviously these all approaches will not be feasible, because we see like the n can go up to 1e5, so we'll not be able to solve it. So first, like, let's analyze how we'll do this means finding out for suppose nums of I, for each nums of I, how we'll find out the number of distinct prime factors. Okay, how now number of distinct prime factors. So we'll be using sieve algorithm for that. If you are already aware about it, then you will be easier to grasp, or we can use it simply as means. Let's see the constraint. So we are given that nums of I can go up to 1e5. So since nums of I can go up to 1e5, for all elements from 2 till 1e5, we'll pre-compute the number of these distinct prime factors in a separate vector, and we'll be able to use it efficiently in constant time for these calculations. Okay, so how we'll do it? So it will be the normal sieve algorithm. We'll simply iterate for I, and we'll be going till this maximum value. Okay, I less than equals to 1e5 I plus plus. Now initialize this means suppose prime of size 1e5 plus 1, and we'll initialize it all these values with 0. Now if when we are at this particular I, if this prime of I is equals to 0, so if prime of I is equals to 0, that means this ith element is a prime number. Okay, this ith element is a prime number, and if it is not, 0, that means it is not a prime number. Okay, so if it is still a prime, means it is prime of I is equals to 0, then for all the elements which are multiple of these i's, multiples of I, so since I is a prime, so all the multiples of I will have I as prime factor, right? So obviously if this ith number is prime, I is prime, so all the multiples of I will have I as the prime factor. Okay, so we can simply iterate through all multiples of I, that is j equals to I till j means j less than equals to 1e5, and we can increase by j plus equals to I. Okay, so we can do that, and we'll see, like we'll simply increase the prime of j by 1. Okay, that means the number of prime factors of j is getting increased by, means this I is the prime factor of j. So we'll be doing that, and the overall complexity of this will be happening in n, and this will be overall n log n. So means we have not used the compute sieve, means complete sieve, because in that case we'll be using this I into I less than equals to 25. We can simply iterate this as well, and we'll be able to pre-compute in n log n. So the concept is like similar to sieve, but we have used it differently here. Okay, so that means according to our constraints. So we'll be able to pre-compute this information. Now each prime of j, means in this prime array, each prime of I will be what? Prime of I will be storing the number of distinct prime factors of this I. Okay, so this pre-computation we have already done, and we can utilize it again in our brute force. Okay, so let's see the code for this sieve algorithm, how we store it. So since like we need to write classes here, so normal int max n and then defining the size is not, means static variables and then using it to define the size of a, means array, is not allowed inside a class in C++. So that's why we have made it static member, so that we are able to do that. So we have made it static, and we are going till 1e5 plus 5, so that we are able to get all elements from 1 to 1e5. We store this prime score, initialize it, means initially it is 0 only. Now if prime score of I is equals to 0, it means I is prime. So if prime score of I is equals to 0, that means I is a prime number. So we will simply iterate through all multiples of I and increase their prime factor count. Okay, so for j equals to I, we will be moving at, means steps of I, and we will be increasing prime score of j by 1, because this I is a prime factor of this particular j. Okay, so this first step is done. Okay, now we know like how we'll be able to find out the prime score of each element. Now comes the main logic of how we'll decide, like currently we are iterating through all the subarrays and square subarrays. Okay, but we need to avoid it to solve it in order of n, obviously, because the constraints can go up to, means constraints are till 1e5, so we need to iterate through subarrays in order of n. So how we'll do that? So we know, like if we have let's see the given input 83938, 83938. So the elements that we'll be choosing as the x, will, means suppose each element, suppose if we consider this element x, it will have a range over which this element will be chosen as what? As the, means the highest prime score, as the x of that particular subarray. So what will the x? We need to find, means for each subarray, what do we need? We need the highest prime score. Okay, so there will be some element x, which will be acting, which will be having the highest prime score over this particular range. Okay, then there will be another element which will be having the highest prime score over this range and this range and this range, so on, such that it covers, means the entire range. So they are x1, x2, x3 and so on, right? So each element will have a range over which it is acting as the highest, means prime score. Okay, means there will be some elements which will not be getting picked up. Okay, so obviously for each means some elements they will be acting as a source of means for each means for all subarrays which include this particular x2 means let it be this subarray, this subarray, this subarray, or starting from here means this subarray, this subarray, this subarray, this subarray, or overlap of both as well, this subarray, these subarrays, and these subarrays, and so on, right? So for all of these subarrays, they this particular x will be acting as the highest prime score candidate. Okay, so what if for each element we find the range over which it is like having highest prime score. Okay, so once we find out this range over which this will be having the highest prime score, then we can try to find out the number of subarrays which contain this I and this element is acting as the prime score. Okay, so once we find out this range, so suppose this range was from L to R. Okay, this is a range that we have. So we have the element L, we have this I, and we have this R. So how do we know like till what range this element will be having the high prime score? Okay, so if this is the element X which is present at ith index, then we need to find the first element on the left whose score is greater than equals to this prime of X. Okay, means prime of this element is greater than equals to X. Why means greater than X? As soon as it becomes greater than X, we know like this will be the element that will be getting picked up. Or if it is equal also, then also we will be picking this particular element, because we know since for equal case we will be picking the element which occurs earlier. Okay, so as soon as we encounter this element such that this prime of element is greater than equals to prime of X, that means this will be like element, so it will having the range from this side. Okay, we'll be able to find out this left range. And what will be the right range? The right range will be simply the prime of element in this case is equal needed, because in this case if prime of element is equals to prime of X, this X will be getting chosen only because X is occurring earlier. Okay, so in this case we will not require this equal case, so we will be only needing the greater than case. So we'll find out the right element on the means the first element on the right which is satisfying that the prime of element, that particular element, is greater than prime of X. Okay, and prime of X denoting is storing what? Is storing the number of prime factors of this particular X. Okay, so we will be able to find these two ranges. Suppose this means this element is occurring at index L and this element is occurring at index R. Okay, so for this I will have these two indices L and R, and now this I will be having the ranges from means it will be equal from L plus 1 till R minus 1. It will be acting as the means the highest prime score candidate. Okay, so what will be the number of subarrays which include this particular I? So it will be simply this I, then I to I plus 1, I to I plus 2, I to I plus 3, and till I to this R minus 1. Okay, and similarly it will be what? It will be from I, suppose, then I to I minus 1, I to I minus 2, I to I minus 3, and so on till I to L. Okay, so these will be the ranges, and along with the overlap of both of these. So what will the overlap? Overlap will be simply what? I minus 1 to I plus 1, I minus 1 to I plus 2, I minus 1 to till R, then similarly I minus 2 till I minus 1, I minus 2 till I plus 2, I minus 2 till I plus 3, and so on till I minus 2, and similarly for L to R. Okay, for L as well, till means all these subarrays. So what will be the candidates for each I? What will be the number of subarrays that will be having for each I? Suppose this. So these L and R are the bounds at which it is means losing its tendency. Means its tendency is from L plus 1 till R minus 1. Okay. So number of candidates it will be simply having is, if we fix the left part. So left part, the number of possible ways of left part is simply the number of ranges from L plus 1 till I. So it will be what? It will be I minus L plus 1 plus 1. So it will be simply I minus L. Okay, the number of elements in the range. So it will be R minus L plus 1, which is simply I minus L. And similarly for right, it will be I to R minus 1. So it becomes R minus L plus 1. So it will be simply R minus I. Okay, so number of ways of putting means including I in the right side is this, and number of ways including I in the left side is this, and to account the total number of subarrays which include this particular I, will be simply multiplying these two ways. Okay, so hence we will be able to know the number of subarrays which means number of subarrays this x contributes is simply what? Is simply I minus L into R minus I. So each nums of I will be calculating these two values, means this left side as well as this right side, and it will be having these many subarrays to which this is contributing. Now what did we wanted? We wanted to find out, means how do we find out this means left as well as right. So before moving on, let's see how will we find out the final result. Suppose we have calculated these two values, and for each element we have its contribution. So we have its contribution. Okay, so for each element from I, for all I, we have this thing. Now to maximize the score by applying at most k operations, we'll be applying, means first we'll be choosing the element which is greater. Okay, so we can simply sort the means decreasing order of elements. While be sorting it on the basis of decreasing order of elements, so that means the element which is maximum is means getting added to our result first, and we'll be adding how many times? Either it will be having the number of contributions it have or the number of k that is left. Okay, so for example, if we had this element 9 and it is having contribution 3 and k is currently 5, and then the next element was 7 and it is having contribution 4. Okay, so since k equals to 5, so first we will be adding 9 3 times. So we'll be adding 9 3 times, 9 into 3 9 3 times, so 9 into 3 27, and in this case what will happen, this k will be getting reduced by 3, so k will become what? K will become 2. Then for this 7 we'll be adding 7 2 times, we'll be adding 7 times, so 7 into 2 equals to 14. Okay, now k will be becoming 0. Okay, so based on this k and the number of contributions each element has, will be means iterating through it on the basis of decreasing order, and then we'll be increasing our overall result. Okay, so in this manner we'll be able to solve this problem. And now how do we like calculate this value, the number of means how many times each contribution? So it will be simply what? It will be n into 3. Okay, so let's first see how we'll be like finding out this left greater as well as left smaller. That's why I told you like we need to be, means the prerequisites for this problem are the sieve algorithm, then binary exponentiation I will be discussing how, and then the prev greater or prev next or prev or next greater element. Okay, so let's first see the prev or next greater element and then we'll see. So first thing was to find the index of prev greater or equal, means we needed to find out the left element such that this prime of element was greater than equals to prime of x. So we need to find, means we look for nearest index j less than I, so that score of j is greater than equals to score of I, and we'll be using this, means doing this in order of n using like a normal stack. So we'll be initializing a stack and pop elements that are strictly smaller than count. So this is the same algorithm that we use to find out the prev greater or prev greater or equal. We modify this less or equal accordingly. Okay, and similarly you will be able to find out this next greater by iterating from the end. Currently we are finding the prev greater, so we are iterating from the start, and finding the next greater we iterate from the end, and we'll simply, since we want the greater, so we'll be popping till it is less than equals to. Okay, so now this will have two vectors, right as well as left, which will be denoting the indexes which stores, means the left range as well as the right range. -1 denotes there exists no index on the left, and right equals to n denotes there exists no index on the right. Okay, now once we have all of these values, then we'll be based on the contribution of each value, how many times it is like getting contributed, we'll be adding it to our result. And we know like we here we did something wrong here, because we are means not adding it, we are multiplying the score, we are multiplying the score at each step. So it will be what? It will be simply 9 into 9 into 9. Okay, in this case it will be adding by 7 into 7. So in this case how many times it will be getting added? It will be getting 9 to the power 3 times, because we have its contribution is getting product 3 times, because we at each step will be multiplying our score by x, and here we will be doing 7 square, we are, because we are means multiplying the score by x, so we'll be multiplying it by 2 times. So now the problem here is to how do we find out this value of, means finding out a to the power b percent mod, because since these results can go up to like very large values, so we need to do mod as well. Okay, so one thing would be to simply for each element we multiply 9 these many times, b many times. Okay, but obviously since the number of k operations that we have can go up to what? N square by 2. So in that case overall the time complexity will again tend to order of n square if we means multiply all these elements in a brute force fashion. Okay, so obviously that is not allowed, hence we need to find out this value of 9 to the power 3 or 7 to the power 2 and so on in means optimal time. So that is where the binary exponentiation comes in, binary exponentiation, which helps us find the value of x to the power y in log 2 of y. Okay, so you'll be able to find out the value of x to the power y in log 2 of y time, and we'll be able to solve this problem. So I hope like you are aware about binary exponentiation. What we do is we convert this y that we power that we have in the form of bits. So for example, if we have 9 to the power 3 here, so it will bits representation will be simply 0011. Okay, so now we'll be increase our result based on these bits contribution, that it will be contributing to the power 0, it will be contributing to the power 1 and so on. Okay, so based on this we'll like do binary exponentiation. So I hope you know about binary exponentiation. This is like the simple code implementation of it. We simply initialize our result by 1 and we will iterate through the bits of y. If y is means if this bit is set, that means we'll be increasing our result by this value, and at each step we move y towards the right, means right set all the bits, and we'll be increasing our result at each step, means this x we getting multiplied by 2 as we move from the LSB to the MSB. Okay, and as soon as we get a set bit, we'll increase our overall result. Okay, so this is the means basic means binary exponentiation which runs in log 2 of y. Okay, and all of these algorithms of pref greater and next greater, it will be running in order of n, and this pre-computation will be running in n log. Okay, so these things we need to be aware of, and once we have all of these values, we'll be simply finding out the contribution of each value, and based on the contribution we'll be updating our result by the element ki power the number of contributions that it will be having based on the value of k, means the number of operations that will be doing. So this will be like the overall discussion, as well as means the overall discussion of this approach. We have saw all the three functions that we'll be using: the sieve, as well as the binary exponentiation, as well as the previous greater or equal and the next greater element. Okay, we have seen all these functions. Now let's see the main function to see how we'll be using all of these values. Okay, so what do we have? We first pre-compute these prime scores. The prime scores is like has been declared global, so we'll be able to access it. So we'll finding out this pre-compute prime scores. Now we store this score so that we are able to find out for each I the first element on left whose score is greater than equals to, and one element on right whose score is greater than this value. Okay, so we find out the scores of I is simply what it will be storing in prime score array. Okay. Now we find out the pref greater or equal and the next greater in these two vectors by calling those two functions which have their own implementation using stacks. Now we find out the contribution. So each element has a particular contribution. So now after we have calculated for each element, we need to sort it on the basis of decreasing order of this element, so that we are processing the means higher value of elements first only. Okay, so we have created this vector of pair which will be sorting it later. So it will be the first value will be value, and the second value will be count of subarrays, means the number of subarrays or the contribution of this element to the number of subarrays it will be appearing as the highest prime score. Okay, now we iterate through each element and see like what is the contribution of each score. So the left count will be simply I minus L, and the right count will be simply R minus I. Okay, and the number of subarrays it will be happening is simply the product of these two values. So the elements of I, for this elements of I, it will be simply what this. We will simply sort it on the basis of decreasing order, and now we will process it while k is greater than 0. So at each step what we will do, we will see like whether k is greater or the number of contribution is greater. So we'll check the number of operations that we will be performing is in the minimum of 2, and we'll be decreasing k by these many operations, and as soon as this k becomes 0, we will simply break. And at each step what we want to increase our result that we have result so far, it will be getting increased by the value e power operations that we are performing, because we are suppose it was 9 and it has a contribution 3, so we'll be updating our result by means the result into 9 to the power 3. So that's why we are calculating this power value which will be running in log 2 of ops. Okay, so we'll be running this, and in the end this answer will be storing the final result of the maximum score. So this is like the overall discussion of this approach. The overall complexity, as we can see, this runs in order of n log n, and these two both of these functions runs in order of n. Then we have these functions which are getting constant result, and we'll be sorting it. So again it is order of n log n, and then we have the contribution. So we iterate through all the elements, it is order of n, and it will be log 2 of ops, which will be overall the operations can go up to log n, so it will be order of n log n here as well. So the overall complexity would be order of n log n, and the space that we have used is order of means a 1e5 here, because of the prime scores that we have used, as well as for the left as well as for the right arrays. So I hope this was like the overall discussion of this hard problem. It was like not, the logic was not much hard, but it was a culmination of these three concepts. So that's why it makes it hard. Okay, logic was not that difficult, but thinking about like means in writing as well as the implementation means together, means combining all of these things makes it pretty hard. Okay, so you should be aware about finding out the prev greater or equal next greater, as well as the binary exponentiation, as well as means sieve is the basic. Okay, so let's try to submit this code here and see how much time it is taking to run. This is the same code that we discussed. We have written all the functions here, and then we have the main function, which will be sorting it first on the basis of contribution values and contributions, and then we'll update our result. Okay, so let's submit this code and see how much time it takes to run. It is running beating 40% of a solution, and most of the solution would be like using the same approach. As we can see, like it is creating a bucket, and based on that it has the prime arrays, and everything is remains the same. We have the binary exponentiation function, and like the code is almost similar only. Okay, so this is like the most optimal approach to solve this problem. I hope you were able to learn something new in this problem. If you are not already aware about these algorithms, then you may have got some idea, and now you can try to means learn about it from different blogs online. Okay, so if you're able to learn something new, then make sure to like as well as subscribe, and if you yet have any doubts remaining in any of the parts, then make sure to comment down. I will be happy to respond. Thank you so much for watching.